The title of the talk is Subsystem Tabulation of a Single Pass Radio Frequency Driver, presented by Professor Helsley. Yeah, let's welcome, please.
Bob apologizes for not being here to present his talk, but he's asked me to do my best to convey what he wanted to say. And I think his slides are pretty self-explanatory. So if I can figure out how to make it work. Basically, some 40 years ago, there was a lot of enthusiasm for heavy ion drivers. And you came up with a design that had a storage ring in it that destroyed your beam quality. And Bob is worried for the past 10 years about how to get that error out of the system. And I want to talk a little bit about that today on his behalf. This is the system that we refer to as a single pass RF driver. Whoops. Sorry. It starts over here with a source area, a linear accelerator, a delay line, another delay line, and eventually the chamber that is driving out here. It starts here with a very large number of beams, and it winds up with 4 beams from each side at the final end. Bob has subdivided this into a whole series of slides. He's given me 3 slides for each of those. I'll never get through them if they don't keep moving. The front end consists of a 64 drivers, each one of which has 16 isotopes. He's used multiple isotopes to make sure that all the charge builds up to the current that he wants at the end, and it's really at the end of the system that you really see that. Each of the panels, you can read them as I speak a little bit. The blue is just a commentary. The green is no problem. Yellow is something that needs to be done. And you can read these as well as I can. But basically, the point is, there's a DC accelerator to begin with. It was initially validated at Argonne a long time ago. And as it goes through the system, the individual ion beams are funneled into a series of 2x2 reductions in number of beams until the beam linac has 4 parallel bores, 4 parallel beams, all the way to the end. And at this point, they merge into a single beam. But that's not the end of the story. So what he's pointing out here is that you reduce every time you go to one of these sections, you reduce the number of beams by a factor of 2 until you eventually get down to these 4 beams that are left. We've been worried about redundancy, and there's probably a little bit need for more, but basically all of this part is green as far as we're concerned. There's a very strong caution here: don't let the emittance grow. Make sure it stays low. And the big change that's occurred since 40 years ago is we now have computers that can do this. Our computers are faster, our timing accuracies at 1 part in 10 to the 10th, that's what your cell phone uses. There's no problem. Okay, looking at the next little piece, he needs to have a means of taking out the space between the microbunches. Each beam consists of an isotopic slug with a whole bunch of microbunches in it, and those get further and further apart as you accelerate it. And he wants to take those out. And he devised an accelerator that basically has a chirp in it as well, so that these beams are forced together. And that's what he calls a snugger, and it basically brings each of the microbunches closer together and then stops them so that they don't continue to creep closer together at the end of the snugger. Basically, the snugger has no engineering physics in it, but there is worries about some of these features like space charge, and there has to be an engineering demonstration that there's not a problem here. So far as we know, no one's ever done that before, and we can't find it in literature at least. If somebody knows something about collapsing a beam in this way, they ought to let Bob know. If you're dealing with multiple isotopes, you want to get eventually to the point where you have a common rigidity, not a common beta. And so the telescoper is a differential accelerator. That is, it accelerates each isotope in a different amount so that they all have a common rigidity by the time they get to the first bend. That means all the isotopes track each other in all the steering magnets. Again, not a problem. Not a problem. These are the issues that have to be looked at, and it's all done relative to the height of study, because the height of study is the most documented driver that we have at the moment. At the end of the LINAC, you have four beams. He represents them here, and he wants to combine them into one. And the idea is, think of these as four beams on the corners of a rectangle, and he wants to combine a pair in the horizontal and a pair in the vertical, and his emittance will grow. That's the only place he allows the emittance to increase. Now that's not really one beam, that's really 8 beams, but they're now in sequence. So the next step is to take those 8 beams in sequence and put them into individual parallel beams 4 at a time again for the rest of the drift line. Again, not a problem with the transverse merger, but it will increase the emittance a bit. The delay lines come next. The first is to take the 8 sequential pulses now that are in sequence and bring them into parallelism again, so that you have 4 going to each side of the chamber. That's done by delaying the first one and bringing the second one up parallel to it, and then delaying that pair, bringing up another pair parallel to those. Straightforward, not a storage ring, but just a delay line. There's a second set of delays that you have to put in, because the isotopic bunches, the slugs he's called them, are far apart. And he wants to take all that extra space out because the whole issue is to get everything to come to a single point at the target. These are the telescoper imparted a different velocity to every set of isotopes. That means they're all now converging. The timing has to be such at the beginning that that convergence ends at the chamber at the target. Let's see. There are some needs for some fast magnets. They are known, but they will have to be documented that they indeed do not create problems. So I talked a little bit about the four slug delay lines. We now have four parallel beams in again, but we now have to take out the spacing between the isotope slugs. And I like his next figure better than this one, but this explains what he's trying to do. And basically it's a sequence in which each color represents another isotope, and there should be 16 colors, but there are only 7 shown here. And you then put these into a delay line. At the end of it, you come out with a very closely bunched set of pulses. This is an awkward thing. I keep touching the wrong button. You have to remember that these isotopic slugs have a whole series of microbunches within them. You have to maintain the microbunches throughout this process. And he points that out here, and it was an early design issue, but we're going to have to make sure that the simulation and the demonstration works right. Otherwise, this is all straightforward accelerator physics. After the microbunches are compressed as much as they can be, we have delay lines, and those delay lines strictly let the isotopes come closer and closer together. The branching you see here, this goes off to one set of driver or chambers, that goes off to another set of chambers, and one of these is the right side and one's the left side. As I said earlier, it's critical the microbunch be maintained in its integrity, and you don't want to let it become a smear. You want a series of pulses the whole way along. That's the way you keep your emittance as small as possible. And at the end, you are going to have a few kilometers from the pellet being over here. You stop maintaining the microbunches, and you let them begin to let the microbunches begin to smear out and become a continuous stream. And then the next step is for the wobbler. And the wobbler's over here. We talked about wobblers earlier. That gives you a hollow beam for the compression part of the beam, and the fast ignition part is actually this part of the pulses, and these are the compression ones. You think that's backwards, but these are moving faster than those, and they converge after it goes through the final focus. They converge on the route between the final focus and the target. I'm going to make it. So we talked, I mentioned there's a final chirp that goes into each isotopic slug that basically forces everything to begin to converge to a single point at the target. And we'll just go on ahead. You know, they begin to all the individual microbunches begin to flatten out, and the last one catches up with the front one by the time you get to the target. I'm sorry, I'm not explaining that as well as I should, but that's the way it's going to be. Well, there is a series of issues here with the focal length compensation. I don't know that I can explain that, but I'll let his words do it. It's a feature that we do have to do a little more modeling on that we have not done as yet. And the final piece is the hollow beam, so that the annulus of the target gets heated. It's a cylindrical target. It gets heated and they compress the center, and at that point the fast ignition beam arrives. Again, the green saying adequately known, the yellow being areas in which he feels we need to do some more analysis. The spot size is about 50 microns in radius. That's what the modeling says we need to have. I recommend that you take a read of the Ramsden Meyer Terrain paper that was published in the spring of 2014. It treats the cylindrical target in great detail and gives you, I think, gives me a lot of confidence that we're pursuing the route that we should be pursuing. Here's his view of the spot radius and the under HIDIF and under SPRFD. You see this big number. That's what the storage did. Your storage range did to your emittance. It really increased the emittance. It made it bad, and it meant you couldn't focus. We think that by maintaining the microbunch structure all the way to the end, we can hold the emittance to about 50 microns. And he writes a little bit about momentum spread here. You guys know more about that than I do. Again, this is the reference that I think that all of you need to be aware of. It's a very nicely written paper in my view, and if you're going to produce energy from heavy ion fusion, I think this is the way you're going to do it. And here's the object of the whole game. This is the pellet. It's like all pellets. It has a tamper layer, absorber layer, pusher layer. The fuel charge in the center. It requires a compression of between 50 and 100. And the fast ignition comes in and focuses because this is a hemispherical surface. That is shown nicely in that Ramsden Meyer Terrain paper. The internal focusing toward the axis. And what more can I say? I think that's probably all I need to say. We tried to get the Department of Energy to fund us on some of this work. We wrote some $10 million proposals. RPE asked us for full final proposals for the high confidence in the pellet. And I asked them to ignite. RPE backed off and said that they couldn't go along. And so there we sit. And that's where we've been since 2012. We think the economics are there. I'll talk more about that on Friday. And I'll be happy to try to answer questions where I have a little bit of knowledge. If Bob hasn't covered it well enough in his slides. I'll be happy to talk in private also. Thank you.
Thank you very much. This time I'm sure only one question, if that's so. Please, Peter. Only one.
I'm interested in getting a longer look at the slide about momentum spread.
Let's see. I would have managed to punch it one extra.
Yeah. Oh, okay. So there's, I guess we should talk offline about what the what the quantitative momentum spread forecast is in the final optics, or was that on a previous slide? I'm sorry if I missed it.
It may have been on the previous slide.
See. Yeah, we'll pick it up offline. All right.
No, I wouldn't, for detailed things like that, I ask that you send Bob an email to RJ Burke at sbcglobal.net.
One question. What is the energy for that target you showed at the very end? The requirement? Yeah, the total
energy.
megajoule per ton.
I'll say it wrong, is my problem. I think this is 20 megajoules.
20 megajoule. Yeah.
Thank you for your talk. So the next